Okay, in the previous two videos, we actually discussed with you that actually the only way for all the S domain, which is all over here, to be stable, and also in the Z domain, alright, that is stable. This is only when we use the testing or the trapezoidal system, the equation, right? Or in other words, for all S to be stable, when we plot all the stable S into the Z domain, which is all inside here, so all of the information in the stability of all the stable S's in the S domain can be plotted inside this Z domain, or which is also stable, which is inside the stable Z. Okay, you get what I mean? So in other words, the outcome is that for all S that is stable, Z are also stable. Okay, and this is something that we want, and this is we have derived the trapezoidal understanding of that, or the bilinear, or testing. There's many names to this. Okay, but however, we say that we have some distortion, alright, distortion that may affect your signal, alright, such that it may not necessarily be, let's say you input your S, alright, this is your analog frequency, this is your digital frequency to some extent, alright. So therefore, later on we will discuss what are all this in terms of their frequencies. But since over here we say that S is stable, when you plot inside the Z also should be stable. But however, for S that plot inside here, the Z may not be exactly the same as the particular S that is being plotted. Alright, this is why we are going to talk about it, and why is there a distortion that occurs. This will be a very subtle one because I don't fully understand the meaning just yet. But I'll just start off with something fairly useful for you. First one is that I want to define S clearly, because S, if you remember, is equals to real plus j omega, right? The real plus the imaginary. However, because we are looking at frequency, so we are only looking at j omega. Alright, but I just want to define properly that the frequency over here is different from the digital frequency. This is why I want to write it as a capital letter omega. Alright, so in the analog system, S is equals to J capital omega. This is your frequency in the analog system. Alright, so I just don't want to confuse you. The next one is this one. Alright, your Z over here, which is coming from here, or here, or here, or whatever, alright, is equals to EJ omega T. Alright, where your this omega, this small capital omega, is your digital frequency. Alright, in fact, I should write this T as not the time, but rather than the so-called the period, EJ omega T. Okay, so this thing over here, what does this mean? In the digital domain, EJ omega T, you take it as theta. For example, omega T is equals to some angle. Alright, if you still remember Euler's formula is equals to cosine theta plus j sine theta, things like that. Alright, so you're going to form a circle. The coefficient, we have some r. The coefficient r gives you the size of the circle. Okay, so in this case we have only one coefficient. This is why we have a unit circle of 1 all over. Okay, so we can represent our digital signal in a whole as this thing all over here. But the key concept I just want to convey is that from now onwards we'll talk about in terms of capital omega and the small capital omega, where small capital is digital frequency, while the capital one is a analog frequency. Alright, and therefore in order to illustrate the distortion issue, I'll just start off with a low pass filter. Alright, in terms of the analog system first. Alright, so I have low pass filter of A over S plus A, and then I rearrange by multiplying with 1. This 1 over A divided by 1 over A is equals to 1. So by multiplying this thing, I somewhat change it to here. Alright, A times 1 over A is equals to 1. Alright, and then S times 1 over A, I have S over A. Then A times 1 over A, you have plus 1. Okay, so I'm just simply rearranging this stuff into this form, because I just want to compare the S as my over the A. Okay, I just want to compare the difference between S and A, where A itself is some cutoff frequency that you want to just input over here. I think I may be wrong, but I think A is some values I think it's the cutoff frequency. Alright, I may be wrong, so take note of that. But anyway, let's continue. But however, because we know that in the S domain, the frequency can be in terms of the positive one all over this side, or we can have the negative one. Alright, so therefore we only want to look at the positive system, so we want to have a somewhat a magnitude. So for example, we have a minus omega. Alright, in order to change it to a positive one, we'll just square it, right? And then after that we do some square root or whatever to find the magnitude. But in this case, we just square it first lah. Okay, so I'll just square everything. So I'll square this, I'll square this thing, I'll square this thing. Therefore, these are all over here. Okay. So what can we do with this information? We are so take note that we are still doing in terms of analog frequency. You see, it's only 1 j omega. And my purpose over here is to illustrate the understanding of a low pass filter. Alright. So therefore, in this case, if my omega is larger than my A, okay, how much output will I have? This is your transfer function. Okay, how much output will I have? How much magnitude of your transfer function will we have? So for example, if I have a omega that is larger than A, so we have maybe for example 3, alright, divided by 1. So omega, clearly this is larger than this. Alright, so 3 divided by 1, I will have 3, and then 3 squared, I will have 9, right? So 1 over 9 plus 1 is equals to 1 over 10, right? Ignore the j lah. Alright, j is just telling you that's the frequency, that's all, nothing much lah. Okay, but I just want to convey the information that the magnitude over here is 0.1 if your frequency is larger than your A. Okay, later on you'll get the meaning already. So I'll just write it as, for example, 0.1. Okay, if omega is smaller than A, then what do I have? So if omega is smaller than A, I put it 1 and I put A as 3. So if I have a 1/3 square, alright, what do I have? I would have 1 over 9. Right, so 1 over 9 plus 1. So this one over here I can choose it as 9 over 9, right? So 9 over 9 is equals to 1. So I would have what? 1 over 10 over 9, which is 9 over 10. Alright, this thing over here is 9 over 10. I'll just flip lah. It's just math only, okay? So therefore I have a 0.9. Okay? So what can we say about this thing? Okay? Is that, okay, I'll just put it down here, 0.9. If your frequency is higher than your cutoff frequency, alright, you'll have a small magnitude. If your frequency is smaller than your cutoff frequency, then you'll have a large magnitude. So in other words, in the frequency domain, alright, and amplitude, this is your low pass. This is where your cutoff frequency lies. Alright. So when your frequency is larger than A, which is somewhere over here, you see your magnitude actually decreases. Correct? But therefore, this is the case where we are looking forward to something. We are looking at the point over here. What is this point such that it starts to actually go down? Okay, there is a point where it goes down. And this particular point is what we are looking at right now. Okay, is that if omega is equals to A, is the half power point. Alright, it's in your PDF. Alright, the whole now what I'm doing is just to write in my own words because, yeah, better. Let's say if omega is equals to A, alright, just now it's all either smaller or bigger. So now if it's equals, then what I have 1 square. This one, if omega is equal to this is 1, this is 1. So I have equals to 1 also, right? So 1 square. 1 over 1 is 1, okay? So therefore I have this thing. So therefore, as you can see, is half. Alright, 1 divided by 1 plus 1 is equals to half. You see? So therefore, in the in the no pass filter, blah blah blah, and then this is the A cutoff frequency. At this particular point, this starts to have a half power already. Alright, somewhere over here after the cutoff frequency, where it is equals to the cutoff frequency, sorry. So what does this mean, half? If I were to change it to decibel, this will ring a bell, because if I have to 10 log base 10, 0.5, you'll have a minus 3 dB. Alright, so the magnitude of, if you take 10 log 0, your magnitude, alright, your this thing over half, you'll get minus 3 dB. Alright, so this half comes from where? Your transfer function. After you have elaborate this one, this you'll have this value, and this value you'll sub it into here to find your decibels. Alright, so this is the point where you have half of your power, and later on you have lesser and lesser powers, and therefore this is the low pass filter. Okay, but however, if you take note, we are still dealing with, in terms of a capital omega, we are dealing with only analog signal, so low pass filter over here is pretty much safe. Before I go to the next video, I'll just do up a question. Okay, I'll just set an initial condition where my omega is equals to 3 and my A is equals to 1. Okay, in such of the case that, sorry, I should have set it as what? I should have set it as A is equals to 1 and omega A is equals to 3, sorry. A equals to 3 and omega is equals to 1. Okay, so if I were to sub omega is equals to 1 and A equals to 3, I will have 0.9, right? Because when A is larger than omega, right? So therefore, I'll just set up this initial condition, where if I have a, because S is equals to J omega, so if S is 1, this means that it's equals to J only, right? Because omega is 1 also. I think you get what I mean? It's directly proportional now. So if S is 2, then it's 2J. If S is 3, then it's 3J. That's the thing. So if I have 1, then it's equals to 1J lah, which is this one. Okay? So therefore, I'll take this initial condition, alright, as my comparison later on. So I'm gonna compare this result. So this is 0.9 after I've put it into here. So what if happened that instead of putting the S as J omega, I put it as my trapezoidal equation. I sub in as 2z minus 1 over tz plus 1. I'll have a slightly different outcome. Alright, I think because I haven't do yet. But let's see how it goes. So see you in the next video.